So lecture number 3 of 4 is about observation impact in data assimilation. And here I'm going to be talking about measuring the influence that measurements have in data assimilation. And then I think this will flow through relatively smoothly into the forecast realm. So the idea is we want to assess what observations do to the analysis and then what the observations do to the forecast. Okay. Yeah, so that's the question. What influence did one measurement or one group of measurements have on the analysis? So we're interested in, if we have one set of measurements, how much impact they have relative to another. We could talk about the aggregate impact of those groups. We could talk about the impact on a per observation basis. So this allows us to compare, for example, radiusons to errors, radiances to whatever other sorts of measurement you care to consider. And like I said, we can consider this also on a per measurement basis. And these two things are often very different. Sometimes very noisy measurements are the ones we have a lot of. So they have the total amount of information they have for us is quite large, even if on an individual basis it's quite small. And I'm going to talk about this in that paleoclimate context that I talked to you about this morning. And what I'm going to show you is that the forward model really matters. How much information we can extract from these paleoclimate proxies depends on how well we model them. Okay, so the background on observation impact goes back to the statistics literature in the 70s and then came into the geophysical statistics literature in the 1990s. And then it really kind of took off in an operational setting with a paper by Cardinali et al., which described how they did this at the RIKEN Center. And I believe it's how they still do it, although I'm not positive about that. And I'll talk about that. I'll review the Cardinali review of the earlier work from the statistics literature. And what this gives is the sensitivity of the analysis that comes from data assimilation in the measurement space. So the impact is measured in that space, which is very useful. We also often want to know what the impact is in the state space. And I have not found much about that. It's mostly this technique which involves the observation space. So I've been working with my colleague Chris Snyder at NCAR about an optimal way of doing this that links the observations and the state, as I alluded to earlier this morning. So I will talk about that theory, and I'll also show you the application of it to the last millennium reanalysis. And here we're going from historical review and some new theory, stuff that's not been published yet, and results that are still kind of in flux. So you wouldn't want to quote any of this. It's still a work in progress, but I'm excited to share it with you. Theory. All right, here we go. And I apologize, I was planning to write all of this on the board, but yesterday I realized, especially for those of you that are not in the first few rows, looking at the whiteboard here was not going to be practical. So I kind of scraped some of my own notes in the draft of a paper, but hopefully you can still make it out in the back, or you can look at the screen. Observation impact is defined by this matrix S as the gradient with respect to the measurements y of the y hats. And the y hats are the estimates of the measurements in the posterior in the analysis. So when we're done with data assimilation, we have an estimate of what the measurements are in the analysis, and we can look at the sensitivity of that to the measurements themselves. And in particular, Cardinali et al., I think in part because it's a very large calculation for the operational system, they're only interested in the diagonal elements of this matrix. That's called the self-sensitivity. And I'll talk about the trace of this matrix in a little bit. You can show that if we take h of 1 where equation number 1 is the Kalman update equation. So that's XA equals XB plus K times the innovation. If we hit that with an H, then that maps the analysis into the measurement space, right? And then so that's very simply, if you take the derivative of that, and I should say there's a little aside here for the students. So we know that linear algebra, matrix algebra, is an important part of data assimilation. It's one of those fundamental tools like probability theory. And it's commonly taught, of course. One thing that I found is not taught as often is matrix calculus. And there's rules that go along with matrix calculus, just like there is for matrix algebra. The rules are not carved in stone. There's just a set of self-consistent rules. I can't go into how I'm using them here, but I think it's a conventional formulation that when I take the gradient of a scalar with respect to a vector, I expect a column vector back. And when I take the derivative of, well, I'll just tell you, if you take d by dy of that equation hit by an h, you get k transpose h transpose. And then if you use the Woodbury formula, if you're familiar with that from linear algebra, you get this expression right here. And ultimately down to this one. So this is the thing that we will work with. So what is it? R inverse. Remember, R is the observation error covariance matrix. So it's normalizing the thing to the right of it. And HA, H transpose, is a covariance matrix for the estimated measurements in the posterior, in the analysis. Right? So this is a square covariance matrix. That's P by P, where P is the number of measurements that we have. And then it's normalized by the error that those measurements had that we assimilated. All right? So we can also talk about, in addition to the sensitivity of the analysis to the measurements, to the observations, we can talk about the other piece of information we have. Remember, we have a prior and we have measurements. We could talk about the sensitivity of the estimated measurements in the posterior to the prior. Right? So these are the two things. Sensitivity of the analysis to the measurements, sensitivity of the analysis to the prior. And if you work through the math, you get this is equal to the identity matrix, which is has the dimension of the number of measurements, once again. So this is the identity. If we have P measurements, it's P by P with ones on the diagonal, minus the S that we saw in the last slide. Where the YE right here is the HXBs. So it's the same thing as the HXAs, except it's in the prior rather than the posterior. So this is before we started the data assimilation. And this is the sensitivity of the analysis to those estimates. So the trace of S, the sensitivity matrix to the measurements, gives the impact of the measurements in degrees of freedom. How many degrees of freedom are explained by the measurements? And the trace of I minus S gives the impact of the background in these degrees of freedom. And if you sum the two of these, the trace of S plus the trace of I minus S, you get the trace of the identity in that space, which is just P, the number of measurements. That's the total number of degrees of freedom that we're trying to explain. And we are attributing a fractional decomposition of the number of degrees of freedom to the measurements that we had and the background. That makes sense? Does it not make sense? All right. I will note that I think, so one of the things you may have heard, or maybe not, but one of the often quoted figures from the Cardinale paper is that when you do this calculation for the ECMWF operational data assimilation system, you find that 85% of this breakdown in degrees of freedom is attributable to the prior, 15% to the measurements. Is anybody surprised by that? You've got, I don't know, 10 million measurements that we're using, and they only contribute to 15% of the impact. 85% is coming from the background. Is that surprising? Not surprising? On the one hand, it's attributed to the prior is a very accurate estimate of the measurements, right? It's a short-term forecast that started from a very accurate analysis, so most of the information is carried from the past. And even though we have all these measurements, they're not telling us very much that we didn't know already. While that may be true, I believe this is tricky to interpret because the prior gets credit for spreading information from one observation location to another, right? So this is where the prior is very powerful. If we have a measurement over here, another measurement over here, when we assimilate this one, we are learning something about this one. And it's, the only reason we know that is because it's mediated by the prior through the covariance. Right? And so that, in this framework, gets attributed to the prior, not to the measurement. So I think it's a little bit hard to interpret in terms of how much influence the measurements have. But it does not affect our ability to talk about the relative role that the measurements play. All right. With that out of the way, before we get to examples, let me talk about this optimal transformation for data assimilation. Again, this is with Chris Snyder at NCAR, my postdoc Dan Amrine at the University of Washington. And the idea here is to transform to a new set of coordinates for both the observations and the state for the prior, where we're going to get linear combinations of the observations. So this is where we're going back to that super observation concept that I talked about this morning, except rather than a straight average, we're going to talk about linear combinations. And linear combinations of the state, such that the analysis that we get from the Kalman filter update equation is rank ordered by the robustness of the relationships between these two linear combinations, right? So we're going to try and find a set of coordinates where we can get the most information out of the observations and out of the state and rank order them. That's the goal. And we're actually going to change variables twice when we do this. We're first going to define x tilde. So x, remember, is the state variable, is the state vector. And we're going to normalize that by the square root of the prior error covariance. Okay? And we're going to do the same thing with the measurements. We're going to normalize them by the square root, inverse square root of their error covariance. And if you do that, you get an equation which looks just like the update equation we saw this morning, except in the tilde coordinates. And I'm not going to show you k tilde because it's an intermediate gain matrix. It's the gain matrix in this tilde space. The more important thing is that the observation operator that maps to this new space is given by this right here. So here's our original h, and the h in the curly space is given by h b to the 1/2. And perhaps the way you might want to think about this b to the 1/2, since this is actually the way it works in practice when I do this is going back to square root filters again, right? So this b to the 1/2 is a square root, and our ensemble sample is an estimate of that square root. Right, so all that ensemble sampling I talked about this morning, those samples are the square root of b. Right, so physically or mathematically the way they're shaped is we have column vectors that are the state vectors for each ensemble member, and we stack them up one after the other. Right, so if we have 100 ensemble members, we have 100 columns. That represents the square root, the estimate of the square root of b. And then we take the outer product of that, so that matrix with the mean removed times its transpose gives you a matrix that's square in the dimension of the state space. That's b, divided by 1 over n minus 1, where n is the sample size. Of course, it's a sample estimate of the covariance matrix, but it only has rank of the dimension of the ensemble. So it's really big, but its effective rank is small.